Hello, this is Mohammed.
Hi, this is Ploy.
Today, we would like to introduce you to fluid friction measurements.
In this experiment, we investigated the pressure drop across an orifice plate and different types of pipes, 2 smooth pipes and 1 rough pipe with different diameters. In this video, we will talk about the method used to conduct this experiment, industrial applications, and will present our data collected. From our experimental results, we were able to calculate the flow rates and the velocity of water through the pipe fittings. These were used to satisfy the objective of the experiment, which was to find the discharge coefficient of the orifice plate and also the friction factor of the pipes.
Now, let's talk about the experimental procedure, which is divided into 4 main steps. The first step is setting the flow rate to either high, medium, or low. That can be done by opening or closing the tap. The second step is placing the foam rubber ball as a stopper. This is to start measuring the flow rate of water. The third step is measuring the water flow rate. This can be done by recording the time it takes for the volume of the water to rise from 0 to 10 liters by observing the volume meter in the tank. The volumetric flow rate is equal to 10 liters divided by the time it took to reach 10 liters. The fourth step is measuring the pressure drop. First, close all valves except the one on the pipe for which the measurement is being taken. Note that in the case of the orifice plate meter, all valves must be opened. Second, the pressure soft tubes coming out of the manometer must be connected to the pipe or to the orifice plate meter, plugging one tube at each end. Finally, the valves of the manometer must be opened and the device switched on by pressing the power button. The manometer will display values that fluctuate rapidly, so an average value of the pressure drop should be chosen and noted down. Repeat the previous steps for the 3 pipes and the orifice plate meter at high, medium, and low flow rates.
Understanding fluid friction and pressure drops allows chemical engineer to determine the design of pumps, valves, and pipe diameters, such that the product moves through the pipes with the required flow rate and pressure, while minimizing the energy consumption. For example, for processes in the petroleum industry, fluids are being moved through straight and coiled tubing under laminar or turbulent flow conditions. Calculations of frictional pressure losses for these circumstances allows engineers to determine how much pressure is needed in the pump to move the fluid through the pipe. Monitoring the pressure drop in a pipe throughout a process could also indicate fouling, which is when solid material deposits on the surface of the pipe during heat transfer and leaks. An example of where this is important in an industry is the design of heat exchangers. Fouling in heat exchangers decreases the cross-sectional areas for the fluids to pass and thus increasing the pressure drop, resulting in a decreased performance.
The following is a sample of our tabulated data. These are the data taken for the orifice plate experiment. The flow rate and pressure drop data are used to produce this graph. This is the flow rate versus the square root of the pressure drop line, and its gradient is used in the discharge coefficient equation. These are the relevant formulae to our experiment. We will only be using the experimental versions shortly. Feel free to use the theoretical version of the friction factor for a smooth pipe or to read that little Moody diagram down there for the rough pipe. No, but more seriously, this is the Moody diagram. The calculated discharge coefficient is equal to 0.66, which is 8% higher than the literature value. This might have been influenced by many factors, including the geometry of the orifice plate, the flow conditions, and the surface roughness. That said, 8% is still considered to be within a reasonable range of the literature value. And these are the friction factor results for the smooth pipe experiment. Notice that the friction factor decreases with high flow rates and increases with the pipe diameter. These observations are directly related to the inverse proportionality of the friction factor with Reynolds number. A higher flow rate means a higher velocity and Reynolds number, leading to a lower friction factor. Similarly, a larger diameter means a lower velocity and Reynolds number, leading to a higher friction factor. And these are the friction factor results for the 17mm rough pipe. The values of the friction factor for the rough pipe are comparable to that of the 17.2mm smooth pipe. This is justified by the fact that the Reynolds numbers of the two pipes are quite similar to one another.
In conclusion, this experiment focuses on studying fluid dynamics, specifically pressure drops across orifice plates and various types of pipes. By calculating flow rates and pressure drops, the orifice plate discharge coefficient and pipe friction factor can be successfully determined. The significance of the results obtained goes beyond the limits of the laboratory, as they offer valuable insights into the real-world applications of fluid mechanics for chemical engineers.